Okay, cool. Welcome to the poster session. So, first we'll have a quick fast forward, and I would ask all of the poster presenters to maybe come over here so that we can run through each one. And the first one will be the conservation of our learned shallow water simulation with differentiable solvers. So please, either use the clicker or.
Okay, thank you for introduction. I'm Naoyuki. Today I will give a presentation on land shallow water equations. Grid-based simulation face a dilemma. Low resolution grids are fast but losses details. On the other hand, high resolution grids can preserve details but computationally expensive. To overcome this problem, we introduce a model that consists of CNN and our differentiable shallow water and renormalization to enforce conservation. Because our model is differentiable end-to-end, it can run a high-resolution dataset effectively. As a result, our method is 2.5 faster than the high-resolution simulation, yet retains the same level of visual detail. Thank you.
Okay, so during my master's degree studies, I've been looking for real-time methods to simulate hair, and I came across some techniques that use position-based dynamics. So what is it about? It's a constraint-based framework to do simulations mainly on particles, but it can also be extended to other types of simulations. And it's very easy to implement and very flexible. And it's interesting because as long as you have the constraint, or you can describe your behavior as a constraint, you can simulate it. So basing our work on previous works, we managed to find a new constraint in which we can simulate hairs and keep its shape using only one iteration per frame. And well, I invite you all to check the poster and see a live demo over there.
Hello, I'm Tomoyo from the University of Tokyo. So we proposed a unified approach to collision detection using signed distances on the vertices and edges. Our proposal can resolve the face vertex contact and the edge contact. And we just use signed distances on the vertices and correct the collisions. And then for edge object test, we use the concept of the gradient and find nearest point on the other object surface and then correct the collisions. So we are looking forward to having discussions in front of the poster. Thank you.
Good afternoon. Our method uses path tracing to update the G-buffer for denoising. And on the
method uses
on the right image is SVGF. Why? Yes, some voice. Our left image is use SVGF, but it has some blurred reflections on the mirror. But our method is use improved G-buffer, and improved G-buffer has more geometry informations and on the G-buffer, so we can get a shape in the reflection. And this is some results. Its path tracing has noise, and SVGF is some blur on the mirror. Is our method. Okay, I jumped it. Okay, thank you. We look forward to meet you at the poster later.
Hello, everyone. My name is Annabelle.
I'm Mary.
And our project is a comprehensive approach to VR-based anti-bullying education. And the quick objective of our project, did that not show up before? Oh, okay, that's the title of our presentation. The objective of our project was to develop an immersive virtual reality simulation software that aims at educating young children on how to effectively recognize bullying incidents and how we provide corrective cues to better their behavior during these situations.
So the things we're measuring for these cues are dialogue.
The things we are using to measure these cues are dialogue, eye contact tracking, social distance, and facial expressions.
And based on how the user reacts during the simulation, we have different outcomes, and it's all dynamic and not pre-programmed. I have a 10-second clip just so you guys can get a little idea of what we mean. Is there sound? No. Let's see. I don't think there's sound on here.
That's boring.
If we get caught, we'll get in trouble.
No way. That's no fun.
Do you want to get in trouble?
No way.
Yeah, so we can show better clips if you guys speak to us during the poster presentation, but that's a quick little demo. And yeah, we'll see you guys soon.
Hi, I'm Bilas. Our poster title is Position-Based Torso Crowds. So the thing is, in traditional crowd simulation methods, the crowds are typically mostly represented as spheres, but these are the not accurate representation of human torso. Basically, spheres overestimate the torso of human, and that in that perspective, we represent capsules. We represent crowds as capsules, where it increases the fidelity and applicability of the application. And we use position-based dynamics constraint, specifically long-range collision avoidance for anticipatory collision avoidance, and also rotation constraint for smoothly change the orientation of the capsule crowds. There are some other previous works where the left on the torso crowd is specific to some dense scenario, and also in the right side elliptical are also a most conservative approximation of human torso profile compared to capsules. And here are some results of our method, where we can see capsule crowds are rotating their torsos and also changing their orientation smoothly while navigating to their goals. I'd be happy to chat with you in front of my poster. Thank you. Yeah, this is the bottleneck scenario, and we can get out of this. Thank you. Sorry. My colleague Yan Hao is looking for full-time position. Yeah, please.
Hi everyone, my name is Xiaoru Liu. Today I want to present our work, Real-Time Reconstruction with Field Probes. Do you remember the time that you suffer from modeling a 3D scene using geometries? It's costly to scale to large scenes, and when we traverse through an environment, it's inefficient to stream scene geometries from a server. So those problems motivate us to use probe data structure. We place a ferro scanner in a real-world scene. The scanner is able to capture 360-degree scene information, irradiance and distance at high precision. Then, using octahedral mapping, we are able to obtain our probe data, which is a 2D image. In practice, we place the scanner at multiple locations to fully capture the environment. Next, we fuse down all sets of point cloud data into a consistent representation. In this way, we can simulate probes at any locations and as many as we want. To reconstruct a scene, we first simulate a grid of probes. Then we find the nearest probes that capture the racing intersections and reconstruct only using those probes. Therefore, the computational cost doesn't scale as the scene size grows. Using our novel probe data structure, we are able to reconstruct a room scale scene in real time. That's all. Thank you.
Let's actually thank the poster authors again briefly.